Alright, this is a quick review of horizontal circular motion. Remember, when you're dealing with something moving in a circle, there is a force required to keep it going, because Newton's first law says the object wants to keep going in a straight path, and since it's curved, there has to be a force that actually pushes it in towards the center of the circle, because it's accelerating towards the center of the circle. That force is called the centripetal force, or Fc, and Fc is equal to m times AC, and AC is just v squared over r. Okay, so a lot of times we actually just go the centripetal force is equal to mass times velocity squared divided by the radius. Okay, and there's a bunch of different problems I can ask you about that, but in the end it usually comes down to this, right? It doesn't matter if you're twirling a rock with a string, the tension in the string is given by this equation, or if there's walls spinning around in a circle trying to force like the water out of clothes in a washing machine or something. Okay, if there's a horizontal circle, then you can ignore gravity because every motion is perpendicular to it, but the centripetal force is towards the center of the circle. Now, there's also vertical circles, and a vertical circle is a little bit more complex because of gravity, and there's just one more step. Okay, and basically it's just like before, you just have to keep track of all the forces. Okay, so now we have a vertical circle, and if we look right here at the bottom of the circle, okay, if this is a rock being swung by a string, then there's a couple forces that act right here. Okay, mass times gravity pulls down here, and the string pulls up, Ft. Okay, but the net force, since this thing is moving in a circle, is actually centripetal force. Okay, and so then if I say then I'm going to say the net force, which is the sum of the forces, so Ft minus mg equals Fc. What I have is the tension force is actually the centripetal force plus gravity, which makes sense because not only does the string have to supply enough tension to counteract gravity, but then it's also got to supply more tension to swing the thing in a circle. Now if we go to the top, up here, then we've still got tension in the string, but we've also got gravity, and this time they're in the same direction. So again, I apply the net force, but now net force equals Fc, just like before, but now the sum of the forces is together because they're in the same direction. So I have mg plus Ft equals Fc, and so I can see Ft is equal to the centripetal force minus mg. Okay? And so, since these are in the same direction, the tension force is actually reduced by gravity. No longer does it counteract gravity, gravity is helping it. Okay, so the tension in the string is the greatest at the bottom and the least at the top. Now we can extend this a little bit further, say with a roller coaster. Okay, roller coasters oftentimes have loops. Now when you're right here at the top, you actually don't fall out of your seat. And the reason for that is because there's two forces acting on you, right? There's gravity, which is pulling down, but there's also the centripetal force that's accelerating you in a circle. And if we just think about this in terms of acceleration for a minute, as long as the centripetal acceleration is greater than gravity, the acceleration due to gravity, then an extra force is actually required, right? Your body wants to keep going in a straight line. That's Newton's first law. This track actually exerts a force on the cart exerts a force on you to keep you moving in a circle. Okay? So as long as the centripetal acceleration is greater than gravity, you're going to be feeling pushed down by your seat. So you're actually not going to try to come out of your chair. Okay, so if I wanted to know the speed at which that happens, the minimum speed. Okay, so basically what I'm saying is if we look right there, instead of tension now it's the track exerting a normal force. I have the normal force plus mg is equal to Fc, right? And basically what we're saying is this force has to exist because the acceleration, the centripetal acceleration over here has to be greater than gravity over here, which means we have to add a little bit to it. Okay, so basically we're saying Fn is equal to Fc minus mg, but the normal force has to be greater than 0. Okay, so 0 is greater than Fc minus mg, and so we get the centripetal force Fc is greater than mg. And then if you sub in everything you know about that, the centripetal force is mv squared over r is greater than mg, and so I get v squared over r is greater than g, just canceled my m's, right? And so multiply by r, and I get v, whoops, that's greater than, v is greater than the square root of g times r, right? That's the slowest you can go and stay in your chair and not need a shoulder harness, but we still want the shoulder harness, okay? And then what if we go the other way? What if there's a road or a roller coaster or something that looks like this, okay? Where are you going to feel the most force? Well, down here you feel the most force because not only does the roller coaster have to support you, or the car, or whatever, it also has to accelerate you up. At the top of the hill you feel the least force because you're no longer gravity, yeah, you're still got to be supported against gravity, but you also have to be accelerated down the hill, right? And so these two forces act against each other. Okay? There's a problem on there that says if you're going over a hill like this, how fast can you actually crest the hill and stay in contact with the road? So you want to keep going straight. Your centripetal force, which is purely supplied by gravity, pulls you down. Okay, so if this is the case, you have two forces. Normal force minus force due to gravity is equal to the centripetal force, but essentially we're saying all of gravity is causing the centripetal force, and if you're actually going to stay in the road, then mg needs to be greater than or equal to fc. We're going to let the normal force actually go all the way to 0, but you'll still be in contact with the road. And so then you get the same equation we had before, but now g is greater than or equal to v squared over r, and so v has to be less than the square root of gr. So before, if we wanted to stay in our chair at the top, we had to be greater than this. Now if we want to stay on the road, velocity has to be less than the square root of gr. Okay? Now there's one more thing I want to take a look at, okay? And that's what happens when we turn a curve on a highway. Okay? When you turn a curve on a highway, if we're looking at a top-down view, okay, the car's right here and you're going straight, and Newton's first law says keep going straight. A few seconds later though, you're right here, you're not going straight, you're going this way. Okay, so you had to accelerate towards the center of the car. So just like before, you have some centripetal force. But if we take a look at this from the back, right, your car is sitting on the road. Okay? And gravity acts down, mg, and the normal force acts up, Fn. What force is responsible for actually allowing you to turn? Well, it's got to be a force towards the center of the circle. It's Fc, but the only thing that can act horizontally here, since we're not speeding up or slowing down, is friction. Okay, so the centripetal force there is going to be due to the static frictional force. Now, if the static frictional force can't supply enough force, instead of turning the corner, you skid, right? So Fc, the maximum Fc could possibly be, is equal to Fs. Okay, and so then what we see is mv squared over r is going to be, and since this is maximum, I'm going to say is less than or equal to Fs, but Fs is really Fn mu s, and so then I get mv squared over r is less than or equal to mg, right, the normal force, since it's on a flat road, mu s, mass cancels, we get v squared over r is less than or equal to g mu s, and so now the only thing that changes is v is less than or equal to the square root of g mu s r, is that coefficient of friction acts in there because it tells us what ratio of the normal force can actually supply some friction. Okay, so that's a pretty straightforward case. It gets a little bit more complex when we think about a banked turn. Okay, and some of your assignment today is going to be about this. If you've got a car on a banked turn, then you've got forces acting in multiple directions. Now, imagine that the road actually curves around like this, right? And so, I'm a horrible artist, but okay. So you're coming around this curve, and what's the idea? Why would we want a banked curve? How could that possibly help us? Well, let me get this stuff out of here. If you look at just the car sitting on the curve, then you can see that yes, gravity acts down, and if this car was at rest, then you would have just the scenario that we're familiar with a block on a ramp, and you would have mgy, and you'd have mgx, and you'd have Fn, and the net force would be 0, right, in x and in y, because the car's not moving, it's just sitting there. But if the car's actually moving around this circular path, then the net force isn't 0. Okay, and in that case, it's easier to keep our x and y like this, because what we're going to have is, okay, the net force in y might equal 0, because it's not going to move up or down the incline, but the net force in x is actually causing this car to move in this circle, so it's the centripetal force. Okay, and so actually what happens is your normal force gets bigger because it needs to supply some of this inward force. Okay, and so then we get the net force in x is Fc, which is actually at a certain speed. You don't need friction to do this. The normal force is big enough. The normal force provides some of that centripetal force, and so we'd have to start summing our forces in the x direction. Okay, and so first I'm going to look right here, and I'm going to say, okay, the normal force has to supply enough force that its x and y components balance. Okay, and this time, wow, let me just go to a new page. I got a whole bunch of stuff going on in there. Okay, so let me come here. All right, so our car's sitting here. Okay, mg is this way, Fc is this way. What speed can we turn this so friction doesn't matter? So we're going to ignore friction for now. Well, the normal force is this way, and it's going to have components. Instead of breaking gravity into components, we're going to break the normal force into components. And you can see when we do this, the normal force is actually bigger than gravity because the y component of the normal force, right, and this time I'm letting x and y be this way, the y component of the normal force is counteracting gravity. So if this is angle theta, then this is angle theta. And so I get mg is equal to Fn times the cosine of the angle. Okay, and that gives me this horizontal side. And that way I can find the normal force, which is good because this side, the normal force in x, Fnx, and this is Fny, okay, Fnx is providing the force necessary to turn the corner, so Fnx is equal to Fc, and so the normal force, which is, well, let's see, how do I find the normal force? Fn times the cosine of theta equals Fny, but that means Fn equals mg divided by the cosine of theta, right? I just solved this equation. Then I can say mg divided by the cosine of theta, but now I want the x direction, so times the sine of theta is equal to the centripetal force, and so I get mg tangent theta equals mv squared over r, and mass is gone, so I get g times r times the tangent of the angle is equal to v squared. And so it's very similar to every other problem we've seen, where we've got gravity times the radius times something, whether it's the coefficient of friction, or in this case the banking angle, the tangent of the banking angle. We're always relating g times r times something to get the velocity of something turning a corner. Okay, good luck with your worksheet today. Let me know if there's any questions.